Hi, I'm Sala, and in this second video we are continuing with our discussion on ellipsoids. In our first video we gave basic definitions and motivation, and in here we will insist on the concept of diagonalization, eigenvector, eigenvalues, and alternative ways of representing an ellipsoid. If we recall our basic definitions, these sums of squares associated to the identity matrix in these inequalities defined the unit sphere. If I scale the identity matrix, as in here, I will get the hypersphere of radius rho in n dimensions. Here we have the quadratic form associated with identity and the unit circle. And if I have a diagonal scaling of my original variables, I get these representations in the new coordinates with a quadratic form associated to a diagonal matrix with positive elements, like this one, which was associated to ellipses in 2D or ellipsoids in a general case, aligned with the coordinate axis, such as this one, in which we stretched the horizontal direction by a factor of 2. The next thing we considered was the possibility of rotating this so that it's not aligned with the axis. So rotations in linear algebra are carried out by rotation matrices, which are orthogonal ones. So if I craft this 30-degree rotation matrix, if in addition to the diagonal scaling, which was stretching in the coordinate directions, I add the rotation carrying out operations, I have this inequality in the new coordinates. Here we have it. So this matrix was defining a new geometric body, which was of course the previous ellipsoid but rotated. And here we have our rotated ellipse. But it's an important linear algebra result that any arbitrary symmetric positive definite matrix P can be expressed as a rotation, diagonal transformation, and inverse of the rotation, which is transposed, so that any positive definite matrix P defines this quadratic form whose level sets, unity level set in particular, is a generic ellipsoid due to the reasons we have just outlined. In fact, as this diagonalization is important, we'll insist on it. If I have any arbitrary matrix, then diagonalizing it, being V the eigenvectors and D a diagonal matrix with the eigenvalues, then I recover the rotation and scaling of the circle that gave rise to the ellipsoid. If we see in Matlab, I had this P matrix that if I don't know where it comes, then diagonalization will recover what we have done here. We have a scaling of the circle, inflating in the first coordinate by a factor of 2, and the 30-degree rotation. But if we start with the P matrix, then diagonalization amounts to tracing our steps backward. Indeed, this is the diagonalization command, in which I get a diagonal eigenvalue matrix and an orthogonal eigenvector matrix. Any symmetric matrix has orthogonal eigenvectors. So P is factorized as this thing, 10 to the minus 15 is just 0. And indeed, these are the eigenvectors returned by diagonalization, and they are coincident up to a sign to the rotation matrix. But okay, that sign is not important because, well, it's easy to check as V is somehow multiplied twice. If I change V to minus V, then I get exactly the same P. And so it happens if I change the sign of any column of V. As ellipses are symmetric, the ellipsoidal shape still holds if I carry out any reflection, and those reflections geometrically amount to, to changing sign of the axis direction, but okay, it's just the same. So we indeed recover the rotation, and of course this diagonal matrix is the same diagonal scaling from which we started everything. So the geometric steps of crafting a circle, converting it to an axis-aligned ellipsoid, and then rotating it can be reversed by the diagonalization procedures in the matrices. Of course, the reversal in algebraic terms is that if I diagonalize and I make this change of variable, then this x transposed px, this is tilde x, and this is tilde x transposed. So with this rotation, we get an axis-aligned ellipse. So this gives insight on the meaning of the diagonalization with symmetric positive definite matrices. Of course, in this axis-aligned ellipse, the diagonal elements were inversely proportional to the square of the semi-axis length. So if I take square roots and invert, I would get the semi-axis lengths. 1 and square root will be 0.5 inverting to the other semi-axis length. So this red line has 30 degrees of slope, and the segment from center to the ellipse boundary has length 2. So good. The next thing we are going to discuss is what happens with ellipsoids which are not centered at the origin. The equations are somehow easy. If I make a translation to some x0, then in here what it has an ellipsoid shape is, of course, this increment of x transpose, so this has an ellipsoid shape around x0. But okay, the thing is that in control, as we usually linearized and call 0 the point around which we wish the state of our control system to be near of, then, well, okay, when we speak, for instance, about, invariant ellipsoids or whatever, there will be no loss of generality in most cases by, just translating to 0 the desired operating point and then forgetting about these more complicated equations and instead just dealing with these in incremental coordinates. So even if we may write the non-centered ellipsoid if we wish so, we usually, in control, will change coordinates so that the center of the ellipsoid is 0. And once that change of coordinates is done, we forget about x0. Also in statistics, for instance, it's quite common to translate the data. If I have a bunch of samples, if I take the mean, translate everything so that my data is 0 mean, then that operation is called centering, and the confidence ellipsoids, let's say, will also be centered at 0. The thing is that both in control and statistics and in many more applications, we just call the center of whatever ellipsoids we are studying, we call it 0 by a trivial change of variables. So we'll forget about non-centered ellipsoids in the sequel. Then, to finish this second video, we are going to discuss other ways of representing an ellipsoid. Which other ways? Well, okay, in some cases we may think that it's a more convenient form representing an ellipsoid with a matrix inverse. Well, come on, it's just the same. I mean, if I denote q minus 1 as p, then it's exactly the same. Of course, you are right that it's a mere cosmetic change of variable. The thing is that if we think in the non-inverted way of writing the equation, then p is inversely proportional to the square of size. For instance, if we call p this thing, then it's inversely proportional to the square of the radius. eigenvectors are the directions of the semi-axis and the length is 1 divided the square root of the eigenvalues. And if we think in the inverted way, if we think on the inverse of P, then are the square root of the eigenvalues and not those of the inverse. So somehow looking at Q, big numbers in Q indicate a big ellipse. So if we wish to have that kind of intuition on the numbers we see in the matrices, then maybe we can, if we wish so, write in the inverted form. But of course, it's just a cosmetic issue. Ellipsoids have the same, at least if we don't take into account some degenerate cases, which we'll discuss in the third video, to keep things simple for the moment being. So for instance, if I'm giving this ellipsoid, then of course this is a sphere with radius 1/3. 9 is inversely proportional to the square of the radius. And if I get this sphere in inverse form, 25 minus 1, then radius is 5. So good, these are inverted and non-inverted representations of an ellipse. Another more interesting representation is as a transformed sphere. I have something U in the unit sphere, and then I multiply it by a matrix L to give me the actual points. So this is U, and after multiplying by some matrix, I get the ellipsoid in some X space. Well, okay, in fact, we already discussed it here with a diagonal scaling and a rotation. But okay, this can just be any arbitrary matrix, and the result of multiplying the sphere by any arbitrary linear transformation is also an ellipsoid. Why is it so? Well, this will be related to the singular value decomposition of L. More on that in next video. For the moment being, let us check that indeed this geometric body verifies the equations of an ellipse. If L were invertible, then U would be L minus 1x. So U transposed U will be this thing. So this X will verify the definition of my ellipse being this P, or I can call L transposed Q if I wish to represent it in inverted form. And P and Q are positive definite because, okay, for any X I wish to imagine, this result is the sum of squares of U. So these expressions I am circling in yellow will render a positive number for whatever X. So I have positive definite matrices in direct or inverted form. So indeed, any arbitrary invertible linear transformation of a sphere renders an ellipsoid. So this is the third way, let's say, of representing any arbitrary ellipsoid. In fact, the linear transformation L can be even non-invertible, non-square, but to keep things simple, we'll leave that for a sequel video. For the moment being, we end here. Summarizing what we have said. We have said that first, it's kind of trivial to define ellipsoids whose center is not 0. Second, we discussed that diagonalization recovers the scaling of a circle to get an axis-aligned ellipsoid, and the rotation V scalings are related to eigenvalues, and rotation is related to eigenvectors. And third, we discussed that there are 3 ways of representing an ellipsoid: in direct form, X transposed Px; inverted form, X transposed Q minus 1x; and as a linear transformation of the unit sphere. The 3 representations are equivalent. We can transform from one another at will if the ellipsoid is not degenerate. And so, with this summary, we end the video here. Thanks for watching.